80 miles off the coast of Oregon, far beneath the cold surface of the Pacific Ocean, the deep ocean floor is quietly tearing itself apart right now. A sudden magnitude, 4.9 rupture snaps through solid rock miles beneath the ocean bed, sending fast seismic waves racing through the water toward the shore. Just 8 seconds later, a second quake strikes right beside the first one, shaking the seabed again before the water can even settle. Nobody on land feels the ground move, no alarm bells ring in coastal towns, and no giant waves appear on the beaches. If you love uncovering the real science behind our restless planet without any fake hype, take 2 seconds to hit that subscribe button right now. By joining our community of curious thinkers, you'll be the first to know whenever deep Earth mysteries break open. To truly understand why a minor earthquake under the ocean has top a scientist paying close attention, we have to look at how our planet is built. The surface of the Earth is not one single solid shell of rock like an eggshell. Instead, it is broken into massive puzzle pieces called tectonic plates. These giant plates float on top of a hot, slowly moving layer of softer rock deep inside the Earth. They're constantly sliding, crashing, and grinding past one another at a speed of a few inches every single year. Off the coast of the Pacific Northwest, 3 distinct plates meet in a very crowded ocean neighborhood. Out under the ocean lies the Juan de Fuca plate, and its smaller partner, the Gorda plate. These ocean plates are made of heavy, dense basalt rock that form from cooling underwater lava. Sitting right next to them is the massive North American plate, which carries the land where millions of people live in Oregon, Washington, and California. Because the ocean plates are heavier than the continental land plate, they get pushed downward underneath the land. This giant underwater collision zone is known as the Cascadia Subduction Zone. It stretches for over 600 miles, running from the northern tip of Vancouver Island in Canada all the way down to Cape Mendocino in Northern California. That is a distance longer than the entire length of California itself. Along this entire boundary, the ocean floor is slowly sliding under the North American continent at a rate of about 1.5 inches every year. That might sound slow, but over hundreds of years, it builds up an unimaginable amount of trapped energy. For a long time, early settlers and geologists believed the Pacific Northwest was a safe place free from giant earthquakes. People noticed that California had famous active faults like the San Andreas, which shook the ground regularly. But in Oregon and Washington, the ground seemed quiet and peaceful. Most folks assumed the plates offshore were simply sliding past each other smoothly without getting stuck. That belief gave communities along the coast a false sense of security for generations. It was not until the late 1980s and 1990s that scientists uncovered clues that completely changed history. Geologists exploring the marshy shores of Washington and Oregon found strange dead cedar trees standing in salt marshes. These trees were dubbed ghost forests because they died suddenly hundreds of years ago. When researchers dug into the soil beneath these dead forests, they discovered a hidden layer of ocean sand buried under the mud. That sand had been dumped miles inland by a massive tsunami. The mystery was solved when scientists checked historical documents halfway across the globe in Japan. On the night of January 26th, in the year 1700, a giant orphan tsunami hit the eastern coast of Japan without any local earthquake warning. Samurai records described a massive wave that destroyed homes and flooded villages. By combining tree ring dating from Oregon with Japanese harbor logs, scientists proved that a magnitude 9 megathrust earthquake had ripped across the Cascadia Subduction Zone. A magnitude 9 earthquake is not just slightly bigger than a normal quake. The scale used to measure energy is logarithmic, meaning every whole number step represents 32 times more energy released. A magnitude 9 quake releases over 30,000 times more energy than a magnitude 5 quake. In 1700, the seafloor off Oregon shifted by 60 feet in a matter of minutes, dropping the coastline by several feet and sending a wave across the ocean. Ever since that massive event 326 years ago, the Cascadia Fault has been stuck tight. The ocean plate keeps pushing forward, but the boundary cannot slide because the friction between the rocks is too strong. As a result, the land above is bending like a plastic ruler being forced into a curve. The coastal mountains are slowly rising and bulging eastward every year as the stress builds up beneath the surface. Did you know that dead trees in coastal marshes helped scientists uncover a giant tsunami from over 300 years ago? If you find it amazing how geologists piece together this ocean mystery, hit the like button and drop a comment below sharing your reaction. Now, fast forward to early August of 2026. Deep under the ocean, 80 miles off the coast of Port Orford, Oregon, automated seismometers detected a sudden spike in seismic activity. At 2:55 in the morning local time, a magnitude 4.9 earthquake shattered rock along the Gorda Ridge and Blanco fracture zone. This fracture zone is a jagged underwater scar where oceanic plates scrape past each other horizontally. Under normal circumstances, an offshore earthquake of magnitude 4.9 would barely make the news. Earthquakes of this size happen regularly along ocean spreading centers where new ocean floor is manufactured by upwelling magma. Scientists usually expect these events to happen in isolation, release a small burst of energy, and fade away quickly without causing any wider effects. But this time, the sequence of events took a very strange turn. Just 8 seconds after the magnitude 4.9 event struck, a second quake, rated at magnitude 4.1, triggered 30 miles away on an adjacent fault line. Double ruptures, occurring within seconds of each other in separate ocean structures, are surprisingly rare. It meant that the stress from the first quake traveled fast enough to trigger a neighboring fault almost instantaneously. That quick 1-2 punch signaled that the stress network on the seafloor was tightly connected and highly sensitive. When ocean geologists pulled the live data streams from offshore instruments, they expected the activity to settle down within an hour. Standard models predicted that a moderate offshore strike slip event would remain confined to the ocean plate without disturbing the main subduction zone closer to shore. But exactly 90 minutes after the ocean quakes, automated land-based sensors in Oregon began flashing with unexpected signals. Small tremors started popping up onshore near Gold Beach and Port Orford, directly along the corridor where the Gorda plate slides beneath North America. What caught the eye of researchers at the United States Geological Survey was not just that quakes happened onshore, but how deep they occurred. One specific quake registered at a depth of 14 miles below the ground. This depth corresponds precisely to the locked interface layer where the two giant plates press against each other with immense pressure. According to official research notes from the United States Geological Survey, small to moderate earthquakes are almost never observed at this specific interface depth. Usually, this deep zone remains completely locked and silent while stress accumulates over centuries. Finding a deep quake right on the boundary line within 90 minutes of an offshore double rupture was an extraordinary outcome that no standard model had predicted. Here's the detail that scientists find most surprising about this whole event. When a deep tectonic system gets disturbed by offshore movement, researchers expect to see a phenomenon called deep slow-slip tremor. Tremors are subtle vibrations produced when deep rocks slip past each other very slowly, releasing energy over days or weeks without shaking buildings. Scientists eagerly checked the regional tremor maps, expecting to see a swarm of vibrations lighting up the southern Oregon coast. Instead, when seismologists loaded the tremor tracking map that night, the southern section of the fault showed absolute silence. Not a single tremor epicenter lit up in the southern zone where the quakes had just taken place. Meanwhile, far to the north off the coast of Washington, 221 tremor epicenters lit up simultaneously. The place that had just experienced 2 earthquakes remained completely locked, while a distant region hundreds of miles away began vibrating. How would you react if you lived along the coast and found out deep ocean faults were shifting 80 miles away? Have you ever felt a real earthquake before? Comment your experience below, and don't forget to subscribe to stay connected with Breaking Earth updates. To understand why this strange silence in the south is so alarming, we have to look at how deep faults accumulate stress over long periods of time. Normally, deep tremor acts like a safety relief valve. As plates push together, slow slip events allow parts of the fault to slide harmlessly every 14 to 15 months, releasing a small fraction of the built-up strain. When a region shows regular tremor, scientists know energy is leaking out gradually instead of building up all at once. When a deep zone shows zero tremor after being shaken by nearby quakes, it implies that the fault is completely locked shut. The friction holding the rock plates together is so high that even a direct seismic shock wave from an offshore 4.9 quake cannot make it budge. Instead of slipping slowly and safely, the rock continues to absorb all the mechanical stress without releasing any of it. That locked friction creates a dangerous pressure cooker scenario deep beneath Oregon. Geologists have mapped the long-term history of the Cascadia Fault by studying core samples taken from the ocean floor. When a giant earthquake strikes, it causes massive underwater landslides that deposit distinct sediment layers called turbidites on the seafloor. By collecting long tubes of mud from deep ocean trenches and carbon dating the organic layers inside them, scientists have built a timeline of every major Cascadia earthquake over the last 4,000 years. The geological record reveals 41 major rupture events in the past 4,000 years. By analyzing the time gaps between these events, researchers calculated that the southern portion of the Cascadia Fault ruptures roughly every 330 years on average. Some gaps between quakes were as short as 200 years, while others stretched longer. But 330 years is the solid statistical average for the southern section running through Oregon and Northern California. Now, consider the current date. The last time the Cascadia Subduction Zone ruptured in a full megathrust earthquake was January 26, 1700. Subtracting 1700 from the present day gives an elapsed time of exactly 326 years. That means the southern Cascadia Fault is now sitting right at the edge of its average historical cycle. In fact, the current silent streak is longer than 95% of all intervals recorded in 4,000 years of Earth history. Notice how closely those two numbers match. 326 years have passed, against an average repeat interval of 330 years. That 4-year difference is tiny in geological time. It is the equivalent of a single tick on a clock that takes centuries to complete. The fault is not just old, it is fully loaded with over 3 centuries of compressed elastic energy that has nowhere to go except into a major rupture. What makes the situation even more compelling is how the southern section differs from the northern section. In the northern part, off Washington and Vancouver Island, full megathrust quakes happen less frequently, roughly every 500 to 800 years. But the southern section off Oregon ruptures much more frequently on its own. Sometimes the South breaks alone in a magnitude 8 event, and sometimes the whole 600-mile fault breaks together in a massive magnitude 9. What do you think is going on deep beneath the Oregon coast right now? Do you believe scientists will soon find ways to predict these deep fault movements accurately? Take a moment to subscribe, give this video a thumbs up, and leave your thoughts in the comments. Pay attention to what researchers are discovering right now about inland faults along the coast. While everyone keeps their eyes fixed on the offshore subduction zone, secondary fault lines onshore in Northern California and Southern Oregon have begun showing strange behavior as well. Over recent weeks, a series of magnitude 4 earthquakes triggered on small inland faults that have no recorded history of major activity. Seismologists refer to these simultaneous offshore and onshore movements as dual-ledger activity. On one hand, you have the offshore ocean plates grinding and snapping against the fracture zones. On the other hand, shallow crustal faults onshore are flexing and popping under stress, transferred from the subducting plate below. When both ledgers show activity at the same time, it means the entire regional crust is under elevated stress. Consider what would actually happen if the southern Cascadia fault were to let go today. It would not be like a standard earthquake that lasts 20 or 30 seconds. A subduction zone megathrust rupture lasts for 4 to 6 continuous minutes of violent shaking. Ground motion would be so intense that standing upright would be impossible. Concrete highways would crack, bridges along coastal routes would drop into bays, and critical infrastructure would lose power instantly. The real threat following the ground shaking is the sea itself. Because the offshore seafloor gets forced upward during a subduction rupture, it displaces billions of gallons of seawater in an instant. That sudden water movement creates a series of massive tsunami waves. Along the Oregon and Washington coasts, the first wave could reach the shore in as little as 15 to 20 minutes after the shaking stops. That leaves virtually no time for official warnings to be issued. In major coastal cities like Portland, Seattle, and Vancouver, the shaking would feel different but last just as long. Because these urban centers sit on soft river sediment and deep basins, the long-period seismic waves from a distant subduction quake would bounce around in the loose dirt. This causes a phenomenon called soil liquefaction, where solid ground temporarily turns into liquid mud under continuous shaking. Tall buildings engineered for short shocks could suffer structural strain from several minutes of rolling sway. This brings us to a crucial question that scientists are working hard to answer right now. Does a magnitude 4.9 earthquake off Oregon mean that the big one is about to happen tomorrow? The short answer from the United States Geological Survey is no. A magnitude 4.9 quake happens regularly in dynamic ocean environments and does not serve as a direct short-term trigger for a megathrust quake. An isolated moderate quake cannot be used to predict an exact date or time for a future megaquake. However, viewing this quake as meaningless would be a major mistake. Earthquakes like the recent one off Oregon act as high-tech natural probes. Every time the ocean floor ruptures, it sends seismic waves traveling through surrounding rock layers. Modern seismometers pick up those waves and measure how fast they travel, revealing hidden details about fault structure, fluid pressure, and rock density deep underground. It is like giving the Earth a CT scan using its own natural energy waves. By analyzing the data from this recent event, oceanographers noticed that fluid pressures in the subduction zone might play a much bigger role than previously thought. Deep within the subduction interface, ocean sediments dragged down by the sliding plate carry trapped seawater under extreme pressure. This trapped water acts like a hydraulic fluid, reducing friction and allowing rock layers to slide. If water pressure rises, it can grease the fault line, making a slip happen sooner. If water escapes into surrounding rock, the fault locks up tight again. If you could ask a top ocean seismologist one question about deep underwater faults, what would you ask? Tell us in the comment section below, and share this video with a friend who loves deep Earth stories. Don't forget to hit subscribe so you never miss our next investigation. Right now, scientists across the Pacific Northwest are upgrading the monitoring networks that keep watch over this restless coastline. For decades, our ability to monitor underwater earthquakes was limited because ground sensors were all located on land miles away. By the time seismic waves reached shore stations, delicate high-frequency details about the offshore rupture had been lost in transit. To solve this problem, teams of researchers have been installing state-of-the-art fiber-optic sensing cables directly on the seafloor. These underwater ocean observatories, like the regional cabled array funded by the National Science Foundation, stretch across the Juan de Fuca Plate. They connect high-speed underwater cameras, pressure sensors, and hydrophones directly to land stations via fiber-optic cables. Scientists can now watch real-time data streaming from the ocean floor hundreds of miles out in the ocean. Additionally, researchers are making incredible progress using a technology called distributed acoustic sensing. This technique transforms ordinary underwater telecommunication cables into thousands of individual seismic sensors. By firing laser pulses down unused optical fibers resting on the seafloor, scientists can detect tiny stretches and squeezes in the cable caused by passing seismic waves. Suddenly, a single submarine cable becomes a continuous line of thousands of seismometers spanning the ocean floor. This real-time technology gives emergency managers precious extra seconds. The Shake Alert early warning system running in Oregon, Washington, and California relies on fast detection near the epicenter. If an offshore megathrust quake begins, seafloor sensors can detect the fast primary waves within seconds and transmit a digital warning to land faster than the destructive surface waves can travel. That warning can automatically shut down gas lines, stop high-speed trains, open fire station doors, and alert millions of people on their cell phones before the heavy shaking arrives. Living near a subduction zone is a reminder of how dynamic and alive our planet really is. Earth is not a static rock floating in space. It is a heat-driven engine powered by radioactive decay deep within its core. That internal heat keeps tectonic plates moving, creates new mountain ranges, forms new ocean crust, and reshapes continents over millions of years. Earthquakes are simply the visible energetic flashes of a planet that is constantly renewing itself. For the millions of people who live along the West Coast, preparedness is the key to living safely alongside this tectonic giant. Emergency agencies across Oregon and Washington encourage families to keep emergency kits ready with water, food, flashlights, and medical supplies. Coastal communities have marked clear tsunami evacuation routes, with bright blue signs leading up into higher ground. Knowing where to walk when the ground starts shaking turns fear into effective action. Every time a magnitude 4.9 earthquake hits off the coast of Oregon, it serves as a gentle reminder from nature. It reminds us that beneath the calm ocean surface and peaceful coastal forests, immense planetary forces are constantly at work. Scientists will keep watching the offshore instruments, tracking the deep tremors, and studying every small quake to help keep coastal communities safe. Let us take a deeper look at the exact mechanics of how subduction zones operate around the world. Subduction zones are responsible for the largest and most destructive earthquakes ever recorded in human history. When we examine famous megathrust earthquakes like the magnitude 9.5 quake in Chile in 1960 or the magnitude 9.1 quake in Alaska in 1964, we see the exact same tectonic blueprint that exists along the coast of Oregon and Washington today. In all of these giant subduction events, two massive plates lock together along a gently sloping fault plane that extends for hundreds of miles. As the subducting plate dives beneath the overriding plate, friction prevents them from sliding smoothly past one another. The upper plate gets dragged downward, compressing like a giant mechanical spring. Over centuries, thousands of square miles of crust bend and flex, storing elastic potential energy in amounts that defy imagination. When the ultimate strength of the rock is exceeded, the locked zone breaks suddenly in a cataclysmic failure. The upper plate snaps back upward and westward, moving dozens of feet in a matter of seconds. This massive displacement of rock transfers enormous kinetic energy into the surrounding Earth, generating powerful seismic waves that travel across entire continents. At the same time, the upward pop of the seafloor pushes the ocean water above it, sending tsunami waves radiating in all directions. To visualize this energy release, imagine bending a wooden ruler with your hands. As you apply force, the ruler bends into a curve, storing energy in its wooden fibers. You can see the tension building as the curve grows steeper and steeper. If you continue applying pressure, the wood will eventually reach its breaking point and snap violently with a loud crack. The energy stored in the bent ruler is released all at once in a fraction of a second. That same principle applies to the Pacific Northwest coastline. Right now, the North American plate is being squeezed and bent inland by the Juan de Fuca and Gorda plates. Coastal land in Oregon is moving eastward at a rate of several millimeters per year, as measured by high-precision global positioning system stations anchored into solid rock. Scientists can track this land deformation in real time, watching the continent deform under the relentless push of the ocean floor. Global Positioning System Network data shows that towns along the Oregon coast, like Newport, Astoria, and Coos Bay, are actively being pushed inland toward the Cascade Mountain Range. The entire coastal margin is slowly rising like a compressed spring. When the fault finally ruptures, those coastal towns will drop downwards by several feet and snap back toward the west. This dramatic shift in land elevation is exactly what killed the ghost forests 326 years ago. Does it surprise you to learn that entire coastal towns are being pushed inland by a few millimeters every year? How would you feel knowing the land beneath your feet is slowly flexing like a giant spring? Drop a comment below and hit that subscribe button to join our community of science explorers. Let us explore how scientists measure and categorize the different types of seismic waves generated during an earthquake. When rock breaks deep underground, it releases energy in the form of two main types of body waves that travel through the interior of the Earth. The fastest waves are called primary waves, or P waves. P waves are compressional waves that push and pull the ground in the same direction that the wave is traveling, similar to sound waves moving through air. Because primary waves travel at high speeds through solid rock, reaching speeds of over 3 miles per second, they are the first waves to arrive at seismic monitoring stations. P waves are usually felt as a sharp, sudden jerk or thud. While primary waves carry energy, they rarely cause severe structural damage to buildings or bridges because they move the ground back and forth in a relatively gentle, longitudinal motion. Following right behind the primary waves are the secondary waves, or S waves. Secondary waves are shear waves that move the ground from side to side, perpendicular to the direction the wave is moving. S waves travel at roughly 60% of the speed of primary waves, meaning the time gap between the arrival of the P wave and the S wave grows wider the farther you are from the earthquake epicenter. Secondary waves are much more destructive than primary waves because buildings are generally designed to withstand vertical forces like gravity, but are much weaker against side-to-side shearing forces. When S waves hit a town, they cause structures to shake violently from side to side. In a major earthquake, this rolling lateral motion can cause unreinforced masonry, chimney flues, and weak walls to collapse within seconds. After body waves travel through the Earth, they give rise to surface waves that roll along the exterior crust of the planet. Surface waves move much slower than P waves or S waves, but they carry massive amounts of energy and produce the largest ground motions felt by people on the surface. There are two main types of surface waves, known as Rayleigh waves and love waves. Rayleigh waves move the ground in an elliptical rolling motion, very much like ocean waves rolling across the sea. When Rayleigh waves pass through an area, the ground moves up and down and back and forth in a continuous wave motion that can make people feel nauseous or dizzy. Love waves, on the other hand, shake the ground side to side in a horizontal plane without any vertical movement, shearing foundations and twisting long structures like pipelines and bridges. In a giant subduction earthquake, surface waves can travel around the entire globe multiple times before dying out. Long-period surface waves are particularly dangerous for tall skyscrapers because the slow rolling frequency of the wave matches the natural resonance frequency of tall buildings. When the frequency of the ground motion matches the building resonance, the swaying motion gets amplified, causing upper floors to swing back and forth across large distances. Understanding these wave dynamics explains why early warning systems like Shake Alert are so revolutionary. Because primary waves travel faster than secondary and surface waves, automated computer algorithms can detect the harmless P wave arrival at sensors near the epicenter. Within milliseconds, computers calculate the earthquake location, estimate its magnitude, and broadcast digital warning alerts at the speed of light to surrounding cities before the destructive S waves and surface waves arrive. For a city located 50 miles away from an earthquake epicenter, a P wave early warning system can provide a 10 to 20 second alert before the heaviest shaking begins. 20 seconds might not sound like a long time, but in an emergency, every single second counts. Automated systems can use those crucial seconds to trigger emergency brake systems on trains, prevent elevators from stopping between floors, shut down industrial gas valves, and alert surgeons to pause delicate procedures. Let us now look closer at the underwater geography of the Blanco fracture zone and the Gorda Ridge, where the August 2026 earthquakes took place. The Blanco fracture zone is a major underwater transform fault system that connects two active seafloor spreading centers in the Northeast Pacific Ocean. To the south sits the Gorda Ridge, and to the north sits the Juan de Fuca Ridge. Along these spreading ridges, hot magma rises from deep within the Earth's mantle, cooling as it meets freezing seawater to create brand new oceanic crust. As new rock forms at the ridge crests, it pushes the older ocean floor outward in opposite directions, like two giant conveyor belts moving apart. The Blanco fracture zone acts as a horizontal strike-slip boundary connecting these two offset spreading ridges, allowing the plates to slide sideways past each other. Because the oceanic crust along the Blanco fracture zone is young, thin, and hot, it behaves differently than the cold, thick continental crust found on shore. The rock along ocean spreading centers is relatively weak and fractured, which means it cannot store as much stress before breaking. That is why most earthquakes along transform faults, like the Blanco fracture zone, top out at magnitudes between 5 and 6, rarely producing massive cataclysmic events on their own. However, the Blanco fracture zone sits right next to the southern boundary of the Cascadia Subduction Zone. Geophysicists have long debated whether moderate earthquakes on nearby transform faults can transfer stress onto the subduction boundary. When an earthquake occurs, it changes the local stress field in the surrounding rock, slightly increasing tension on some neighboring faults while relaxing tension on others. This process is known as static stress transfer. When a fault is already near its breaking point after hundreds of years of stress accumulation, even a tiny increase in stress from a nearby earthquake can theoretically act as a trigger. Seismologists carefully calculate these stress changes using complex computer models to see if offshore ruptures bring the Cascadia fault closer to failure. While a magnitude 4.9 earthquake creates a relatively small stress change, its close proximity to the subduction interface makes it a subject of intense study. Have you ever wondered how scientists map invisible faults buried miles under the ocean? If you are fascinated by underwater geophysics and want to learn more about ocean discoveries, leave a comment below and make sure you're subscribed to the channel. Let us also explore the fascinating history of how underwater seismology evolved over the last century. For decades, studying earthquakes beneath the ocean was one of the most difficult challenges in earth science. Land-based seismometers could detect large ocean earthquakes, but smaller events went completely unnoticed because seismic waves lost energy as they traveled through hundreds of miles of water and crust before reaching land stations. During the Cold War in the 1960s, the United States Navy built a secret network of underwater microphones called the Sound Surveillance System, or SOSUS. The original purpose of SOSUS was to track foreign submarines moving through the deep ocean by listening for the acoustic sounds generated by their propellers. Arrays of hydrophones were anchored to the seafloor across the Atlantic and Pacific Oceans, connected to land processing stations by miles of heavy cable. In the early 1990s, after the end of the Cold War, the Navy allowed civilian scientists to access the SOSUS network for environmental and geological research. When seismologists began listening to the deep ocean hydrophone data, they were amazed by what they heard. The ocean was not quiet. It was filled with rich acoustic signals, including underwater volcanic eruptions, deep earthquake swarms, migrating whale calls, and calving icebergs. Hydrophones are uniquely suited for detecting underwater earthquakes because seismic ruptures transfer low-frequency sound energy directly into the water column. These acoustic waves, known as T waves, travel immense distances through a natural ocean layer called the SOFAR channel. The SOFAR channel acts as an acoustic waveguide, trapping sound waves between layers of varying water temperature and pressure, allowing low-frequency sounds to travel thousands of miles without losing energy. Using hydrophone data from the SOSUS network, scientists discovered that the ocean floor off the Pacific Northwest was far more active than land-based sensors had ever revealed. Researchers detected thousands of tiny earthquakes and volcanic swarms along the Juan de Fuca and Gorda ridges that had previously gone completely unnoticed. This groundbreaking discovery revolutionized our understanding of how ocean crust forms and how underwater fault systems interact. If you found this deep exploration of Earth science enlightening and inspiring, please take a moment to subscribe to our channel right now. Turn on the notification bell so you never miss a breaking story. Drop a comment letting us know your thoughts on the Cascadia fault, and share this video with anyone who loves real science and natural mysteries. Thank you so much for watching. Stay safe and keep exploring until next time.